Hi, welcome back for another edition of Jensen Doing Calculus. Today we're working on problem B5. This is your second edge elastic problem of the week. As we get warmed up and ready for that, we'll open you guys up with another joke today, and then we'll get into it. So here's my question for you today. What is the best part of Switzerland? I don't know either, but the flag's a big plus. Woo! All right. Well, hopefully you got over that. By now, most of you guys have learned that the first 30 seconds of video I'm telling you guys a joke, and so most of you guys are just hitting that like fast forward 30 seconds to get into the real math. Today, here we go. We're getting into particle motion, okay, or straight line motion. So we have this X of T, which is giving our position of the particle at any given time. We can determine the position of the particle using this piecewise function. Whether t is between 0 and 1, we're using natural log of kt, or if t is greater than or equal to 1, we're using this one, t times cosine of 4 pi t. And they've asked us to do a whole plethora of things. We have 5 parts again to this problem. And so, what we're going to do is we're going to get into it. We're going to get into part A. For part A, what they've asked us to do is define v of t. Now, on these problems, they've asked me to do a lot here. Normally, we can, if we're working with polynomials or regular functions, we can just have this assumption that the functions are differentiable, unless we're working with something that could be like a graph, where we're looking for things that are, we're lacking on the differentiability of it. So something like where the function is no longer continuous, or that our function does something weird where the slope is like our function forms like a corner or a cusp or something like that. I personally don't think they would get this technical on a problem like this on the AP test, but I'm going to talk about what would be necessary to take this derivative. Define v of t. I need to take the derivative of this one, and I also need to take the derivative of this function. However, at t equals 1, because this is a piecewise function, there's a few different things that we have to then check. The first thing we'd have to check is the function continuous at 1? The way that we would check continuity is we would check is the limit from the left at 1 equal to the limit from the right at 1 equal to the function's value at 1. If all three of those are lined up, then our function is continuous. Then, to show that it's a differentiable, I need to show that the slope that this is approaching at 1 is the same as the slope as this is approaching at 1. So I'd have to use definition of derivative to prove that, or I take the derivative and then substitute 1 into that. I believe that the intent of this question was for us to check some of that stuff way down in part E. Otherwise, I got to check for differentiability for v of t, and then I have to do it again for a of t when I get to b. So because of that, I'm going to go just by finding the derivative of each piecewise function, and I'm going to make an assumption there that it's differentiable. To find v of t, I have 2 parts. I have when 0 is less than t is less than 1. If I want to check if it's differentiable here, I'm going to consider that function x of t is equal to natural log of kt. So we take the derivative of natural log. This is going to involve our chain rule. So my inside piece is kt. And so derivative of natural log would be just 1 over x, or in this case it's 1 over kt. So the derivative would be v of t. And that would be 1 over k of t. But because the inside piece would involve chain rule, we have to take the derivative of the of this term kt. And the derivative of kt would just be k. Remember, we're taking the derivative, and I probably should have written this, we're taking the derivative with respect to time. We're taking d dt of both sides. When I get this, then I get v of t is equal to k divided by kt. And we'll see then for v of t that these k's can divide out. And so v of t is equal to 1 over t. And so this is what v of t equals when t is between 0 and 1, because that's my first piece. So then my second part is now when t is greater than 1, okay, or equal to, I'm using this function for my x of t. So then x of t is equal to t cosine of 4 pi t. Again, I'm going to take the derivative with respect to time. Showed my d dt of both sides. The derivative of x of t is x prime, or we're going to call that v of t. And then here, the derivative of this is going to first involve the product rule, because we have two separate functions being multiplied. So we use our product rule definition. And then when we take the derivative of this second piece here, it'll also involve the chain rule. So let's see if we can go through this. Product rule, I'll do the derivative of the first times the second. So derivative of t is just 1 times the second cosine of 4 pi t plus the first function, which is t, times the derivative of the second function. Derivative of cosine, remember we're going down, cosine is so cranky, so he changes signs. So cosine goes to negative sine of 4 pi t times the chain rule says that if we take the derivative of something with a function inside, our inside function is 4 pi t, so the derivative of 4 pi t is just going to be 4 pi. When we do this now, we're going to clean this up a little bit, and I get v of t is equal to cosine of 4 pi t. 4 pi times t is 4 pi t. With the negative there makes this a negative 4 pi t times sine of 4 pi t. So at this point now, we're able to get v of t. Defined when t is between 0 and 1, and when t is greater than or equal to 1. I could write this again as a piecewise function, but the way I've laid out my work means I don't necessarily have to do that. Alright, we're back here for the part B. So in part A, I found v of t. I've written it up here in blue. I wrote it as a piecewise function in case you wanted to see what it would look like as you wrote it that way. For part B, what they've asked me to do is to find a of t. I know that a of t means the acceleration, or the derivative of the velocity. So I need to take the derivative of the velocity, which means I'm taking the derivative of each piece here. So I've set it up now, when t is between 0 and 1, I'm taking the derivative of my first piece. And when t is greater than or equal to 1, I'm taking the derivative of the second piece. So here we go. The derivative of the first one means I'm taking d dt, the derivative with respect to time of this function. That would give me v prime, or we can write that as a of t. This would be d dt. I like to write 1 over t as t to the negative first, like that. The derivative of this would then end up being negative t, and I subtract 1 from that, so negative 2. And this would equal negative 1 over t squared. And so this would be a of t. And so this is relatively straightforward to find a of t here for this function. Now when I want to find a of t for this function, I have to take the derivative with respect to time of this. So I need to take d dt of this function. When I do that, I have two separate pieces that I can take the derivative of. On this piece, we will end up using the chain rule. And on this piece, we'll end up using the product rule, and in addition to that, the chain rule. So we got a lot of stuff going on. We just want to make sure we lay out our work very clearly as we go through this. All right, so the first part, derivative of v of t is a of t. That's the easy part. Equals the derivative of cosine of 4 pi of t. Take the derivative of cosine. Remember, cosine is so cranky, so when we go down, he always wants to change signs. Cosine goes to negative sine of 4 pi t times, we have to use the chain rule. The derivative of the inside piece would end up being derivative of 4 pi t, which is just 4 pi. So that's my first piece. Now I'm going to my second piece. I'm taking the derivative of. In this case here, I have now the product rule. So I'm going to take the derivative of the first function. The derivative of the first piece would be the derivative of negative 4 pi t. So that's going to be negative 4 pi times just the second. So this is like u prime v. So times the second would be just times sine of 4 pi t plus the first function, negative 4 pi t. 4 4 pi t times the derivative of the second. So now I need to take the derivative of sine of 4 pi t. The derivative of sine remember, sine is so happy, so when he goes down, he goes to cosine. He doesn't change signs. So derivative of sine goes to cosine of 4 pi t. Oh, I opened a parenthesis. Let me close that parenthesis. Sorry, cosine of 4 pi t times the derivative of the inside. This is where I'm using, when I'm taking the derivative of just this portion right here. I got cosine of 4 pi t, and then times the derivative of the inside piece. So the derivative of 4 pi t is just going to be 4 pi. So now my goal is to clean this up. When I do that, I get a of t equals to the first one. This 4 pi is not, I'm not taking the sign of it, so I can write this as negative 4 pi sine of 4 pi t. This second piece, there's nothing else I can do here, so I can write it as negative 4 pi sine of 4 pi t. And then for this last piece here, I have 4 pi times negative 4 pi t. So that's going to be negative 16. Negative 4 times positive 4 is negative 16. Pi times pi is pi squared. And then this t is still here. Times cosine of 4 pi t. So this is a of t for the second piece here. I could go further. Again, once we get to a spot that would satisfy it for the AP test, we would normally encourage you guys to stop there. So for that, normally I would tell students, if you're not going to use a of t later in the problem, I would have stopped right here before doing any simplification. However, because I've looked ahead and I know I'm going to end up using a of t in this problem, I'm going to simplify this just one step further. And here's what I'm going to do. I got negative 4 pi sine 4 pi t and negative 4 pi sine 4 pi t. That's going to be negative 8 pi sine of 4 pi t. Then minus 16 pi squared t times cosine of 4 pi t. So I was able to combine these two terms because they were both in terms of sine 4 pi t. So I have that, and I've gotten a of t now for this function. Alright, welcome back. Here we go for part C here. So you'll notice what I've done on the whiteboard, just to maybe clarify a little bit or leave it so it's clearly communicated. I have my X of t function, that's the original. From part A, here's my V of t, and from part B, here's my A of t function. On part C, here's what they've asked me. They want to know whether the particle is speeding up or slowing down when the t equals 3/2. We don't have a graph to look at here, so we're going to try to do this based off of a function, based off of equations. So algebraically, or conceptually, let's talk conceptually first. Conceptually, a particle is speeding up or slowing down depending on its velocity and its acceleration. In short, if the velocity is positive and the acceleration is positive, that means in this case our particle is going to the right and it's speeding up, that the acceleration is also going to the right. So we would be speeding up. So if velocity and acceleration are going this way, or they're both positive, we're speeding up. Also, if velocity is negative and acceleration is negative, then I'm also speeding up because my velocity is this way and my acceleration is pushing me this way. However, I'm slowing down if my velocity and acceleration have different signs. So if my velocity is positive, like I'm going this way, but my acceleration is negative, that means I'm going this way, but I'm slowing down. And then vice versa, if my velocity is negative, but my acceleration is positive, then again I'm slowing down because I'm going this way, but I'm slowing down because the acceleration is pushing me back. So what we're looking for is, are the velocity and acceleration both positive or both negative or 1 and 1 at t equals 3/2. So at t equals 3/2, we need to find then, our goal is to find v of 3/2, and then our other goal will be to find a of 3/2. For v of 3/2, I need to put 3/2 into my v of t function. Since 3/2 is like 1.5, that's a number that is greater than or equal to 1. So I'm going to put 3/2 in here. And so we're going to do, that's going to be cosine of 4 pi times 3/2 minus 4 pi times 3/2 times sine of 4 pi times 3/2. I'm going to erase this for now just so we're not confused. 3/2 times 4 pi. We multiply fractions, we can multiply across, or you can divide out first. That's going to be 12 pi divided by 2, so that's 6 pi. So essentially we're doing then cosine of 6 pi minus 4 pi times 3/2. Again, it's going to be 6 pi times sine of, this is going to be 6 pi. So now I need to think, where is 6 pi so I can evaluate cosine and sine of them. Well, 6 pi in the unit circle, 2 pi is a full lap, so 6 pi is 3 laps around. We're back at essentially our starting point, or at 0 radians, where the coordinates are 1, 0. Remember, cosine will give me my x value, and sine will give me my y value. So cosine of 6 pi is the x value here, which should end up being just 1, minus 6 pi times sine of 6 pi is the y value there, which is 0. And 6 pi times 0 is 0. 1 minus 0 is 1. And so we got v of 3/2 is equal to 1. Here. Most importantly, we just care, is that number positive or negative? It's positive. So our velocity is going this way. We need to now see, is our acceleration also positive, in which case we're speeding up, or is my acceleration negative, in which case then they're going in different directions, so we're slowing down. So I'm going to erase this part. We're going to leave v of 3/2 equals 1 because of space that I have on my whiteboard. So when I do that, I get this here, erasing this part. Obviously, don't erase your work on the AP test unless you know it's wrong. But here now I have a of 3/2 is equal to, I'm putting 3/2 in for t into this function, so this is going to be a lot longer of a line here. Negative 8 pi sine of 4 pi times 3/2 minus 16 pi squared times 3/2 times cosine of 4 pi times 3/2. So I'm putting in 3/2 everywhere I see t for a of t. Again, I'm using the bottom function because that's when t is greater than or equal to 1, and t in this case is 3/2. So here this is going to be negative 8 pi times sine of 6 pi, because that's 6 pi, minus 16 divided by 2 is negative 8 pi times 3 is going to be negative 24 pi squared times cosine of 6 pi. So when I go ahead and do this, sine of 6 pi, just like it was before, we're still using 6 pi is still the point 1, 0. Sine is still going to be the y value, so the y value there is 0. So 0 times 8 pi is just a big fat 0. Minus 24 pi squared, I need to do cosine of 6 pi. Well, cosine of 6 pi would be the x value there. The x value there is 1. So all of this is 1. So 1 times negative 24 pi squared is negative 24 pi squared, which is negative 24 pi squared. Most importantly, we don't necessarily care a ton about what this number is, because they didn't ask me to find a of 3/2. All I need to know is this value positive or negative? And we can clearly see it's negative. And so because my velocity is positive and my acceleration is negative, then my particle is slowing down. And so that's what I want to write. So I'll write something, maybe I can fit it in here. Since v of 3/2 is greater than 0, and a of 3/2 is less than 0, the particle is slowing down. And that's our answer for part C. Alright, so we're back for part D. For part D, here's what they've asked us to do. They've asked me to write, but not solve. Importantly, thank goodness we don't have to solve a single, and this is a highlight, I would highlight that word, a single trig function where the particle is at rest. So, or maybe it was equation, but we're trying to find a single equation where the particle is at rest. Remember, the particle will be at rest when v of t, the velocity, is at 0. Because when my speed is 0, that's when my particle is at rest. So we need to find out when that's true. In my opinion, here's what I would go after. I would say I'm going to take each piece, set them equal to 0, and see if I can set up an equation to solve them. For the first piece, when 0 is less than t is less than 1, that would be when 0 equals the first piece of my velocity function, 1 over t. But in this case, there's no t value that we could put in here between 0 and 1 that would ever make this true. Because notice if you multiply both sides by t over here, you're going to get 0 equals 1. And so that's not possible. So then this is never true. So this it's never at rest. So never at rest here. And so that's the first part. So the first we go, okay, then the second part, maybe that's where it's possible. So the second part is setting v of t equal to 0 for the second piece of this function when t is greater than or equal to 1. So I would write when t is greater than or equal to 1, v of t equals 0 would be when 0 equals cosine of 4 pi t minus 4 pi t sine of 4 pi t. Now, some of you guys may be tempted, kind of like I am, to put your hands up and go, well, that was a tough one. Done, moving on. However, they clarified that they want me to set up an equation that has a single trig function, meaning I can only have one sine or one cosine or one secant, for example. And so right now this has 2 different trig functions, so we need to find a way to combine those. So the way that we're going to do that is I'm going to add this term to the other side of the equation. When I do that, this is going to be 4 pi t times sine of 4 pi t equals cosine of 4 pi t. And so now I have a trig function on each side of the equation. And now if I divide both sides by, I can divide both sides by sine of 4 pi t or cosine of 4 pi t. Both of them will give you slightly different looking answers, but both would be correct. If I divided here by sine of 4 pi t to both sides of my equation, then notice on the left side here, these will divide out and I have just 4 pi t left over. And on the right side, because these angles are exactly the same, then we can think of a function that relates cosine over sine. If you go back to our trigonometry days, I know your pre-calculus teacher was just amazing and wonderful and really good looking. And he probably taught you that cosine divided by sine is cotangent of 4 pi t. So at this spot here now, I have an equation. It's not solved yet, and thank goodness we don't have to solve this, that involves a single trig function. And so therefore I have now answered when the particle would be at rest is this equation that I would need to solve. Okay, we're back for part E. For part E, what we're trying to do is find the value of k such that the velocity, notice this word wasn't there the whole time, the velocity of the particle is continuous. We're trying to find the value of k such that the velocity of the particle is continuous. I wrote some notes up here. In order for the velocity to be continuous, the v of t function must exist. Okay? Now we've already written the v of t function, but there's something we needed to check for that I kind of alluded to in part A, but I'm addressing all the way down here in part E. In order for v of t to exist, x of t has to be differentiable. Like I said, normally we're working a lot lately with polynomials, and so differentiability is not assumed, but it's just we don't work with many things that aren't differentiable because we can't do a lot with it. And so we know that the natural log is differentiable, and we know that some sort of polynomial, even with the trig function, that the domain is everything, is also differentiable here. And so we want to see is x of t differentiable. In order for x of t to be differentiable, we need to check 2 things. first thing we need to check is we need to check that x of t needs to be continuous. That if our function is not continuous, then it's not differentiable. And then the second thing, x of t needs to be differentiable at the point in question. In this case, this is where the two piecewise functions meet. So we need to check if it's differentiable at t equals 1. Okay? At t equals 1. And so if we can figure out if these are true, then we will be able to find a k value that would make our velocity continuous, that we could draw the entire velocity function without lifting our pencil, so to speak. So these are the two things that we need. So let's first work on x of t being continuous. Okay, so that's what I'm going to work on first. That x of t would be continuous. Actually, I don't even need a of t here, so I'm going to erase that, give myself a little bit more room. Okay. So x of t, then, for x of t to be continuous, at t equals 1, that's the point in question then, we need to see that the limit, that as x approaches 1 from the left of x of t is equal to the limit as x approaches 1 from the right of x of t. I can't write x of t for whatever reason. And that equals then, both of those need to equal the actual value at 1. So that needs to equal x of 1. Okay? So all three of these have to be true. Okay? So in the first one, here the limit as x approaches 1 from the left of x of t would be, this would be natural log. We could try direct substitution here. We're going to put 1 in here. So natural log of kt would just be 1 times k, so this is natural log of k, equals, limit as we approach 1 from the right means I'm using this function, so I'm putting 1 in for t here and here, so that's going to be cosine of 4 pi times 1. And then, in this case, x of 1 is going to be the same thing as this function. So this part is already satisfied and absorbed in here. So now we need to evaluate this and see what value of k would make the function continuous. Here, this is still natural log of k equals cosine of 4 pi. Remember, 4 pi is going to be 2 full laps around, which is the same thing as 0 radians or 2 pi radians. So the point is 1, 0, and cosine of 4 pi would be the x value there. So the x value there is 1. So then now we need to figure out a value of k that would make this true for our function to be continuous. We need to solve for this. This is where we're going to use our good old-fashioned swoopy-doop. Log base e of k equals 1. This would be e to the first equals k. And e to the first is just e. And so I get k is equal to e. Okay. So this is the value that I would want for k to make the function continuous. Now, the next thing I want to check is whether or not my function is differentiable. To check if it's differentiable, I need that the slope of this function when t is equal to 1 is equal to the slope of this function when t is also equal to 1. That if it's not a smooth curve, then, for example, if my slope here, let's say when I put in 1, became negative 1, and my slope here when I put in 1 became positive 1, my function, if it made a sharp corner, this function would not be differentiable. So we need to check the slopes of each of these. Luckily, we've already have the derivative, so we're going to write it this way. Okay? I'm going to write it. I'm going to erase this part, and I'm sad about it. But you guys can always go back. We know that k equals e, and so now we're going to check whether it's differentiable at 1. So we need to see that x of t is differentiable at t equals 1. And so when we have that, then we're going to be looking for this, and that would be to say that differentiability involves the velocity. So I need then that v, that the limit as t approaches 1 from the left of v of t is equal to the limit as t approaches 1 from the right of v of t. I should have written t on my limits for the last one. I think I put x there. So when I do that, the limit as t approaches 1 from the left would be using my velocity function. Putting in 1 here is what I'll try direct substitution first, which would be then 1 over, when t equals 1, would be 1 over 1. And here, when I put in 1 into the second function here, would be cosine of 4 pi t, which is 1, minus 4 pi times 1 times sine of 4 pi times 1. So 1 divided by 1 is 1. And then cosine of 4 pi, we just did this, remember that was the 0.10. Cosine means I want the x value there, so that would just be 1. Minus 4 pi times 1 is 4 pi. Sine of 4 pi is the y value at 4 pi, which would be 0. So 4 pi times 0 is 0. And so I get 1 equals 1. What I've shown now is that my function is continuous and differentiable, and with a k value of e, that will end up making my velocity continuous. So there's a lot going on there. Hopefully you're able to pick all that up and that you're able to solve this problem. If you would do me a big favor, put a big thumbs up right below, and you guys would have a wonderful day. I'll talk to you guys later.